Good day, and welcome to our webinar on IIoT and edge computing architectures, including use cases and lessons from the field, brought to you by CFE Media and Technology and sponsored by Maynard, Massachusetts-based Stratus Technologies. Today we'll be joined by Ed Kuzemchek, Chief Technology Officer, Director of IoT, and founder of Software Design Solutions, and by Jeffrey Young, Head of Business Development Americas at Stratus Technologies. I'm Kevin Parker, a Senior Contributing Editor with CFE Media. Thanks for tuning in to what's sure to be a very interesting presentation and discussion. Gartner says that by 2022, more than 50% of industrial IoT analytics will take place at the edge, up from less than 10% today. With IIoT projects becoming more popular, OT and IT engineers require project specifications that decrease overall complexity, minimize CapEx, OpEx costs, and reduce risk. In response, engineers are designing, building, and maintaining more operationally simple, high-performing, and secure computing architectures. Stay tuned for an informed discussion about IIoT computing architectures for machine, line, plant, and enterprise applications, including specific use cases, challenges and benefits, as well as the technology's continuing evolution. To get the best results from the webcast platform, please make note of the following as you participate in today's event. If you are having technical problems, click on the question mark at the top right-hand corner of your screen to bring up a list of system checks to make before escalating to an online technician. If you are experiencing issues with your slide or audio, please refresh your browser or click the Refresh Media button directly under the presenter's headshot. You can control the volume settings of this webcast by adjusting the volume on your computer or by adjusting the volume on the webcast platform. If you do need a technician, type a message into the Ask a Question box and someone will get to you as quickly as possible. Answers to your technical questions will be in the Answered Question box on the left-hand side of the screen. The Ask a Question box is also used to ask the speakers questions. You may ask questions at any time during the presentation. We'll get to as many as time allows. To download the presentation slides and certificate of completion, use the Event Resources box on the left-hand side of your screen. You can download the presentation and certificate of completion until the conclusion of the webcast. The link will break when the webcast signs off. This webcast is being recorded, including the Q&A session. We'll send you an email message within a week with a direct link to the webcast archive. For those of you who might be relatively new to the subject matter, here are a few brief definitions of computer concepts central to today's webinar, including for edge computing, cloud computing, fog computing, and big data. I'd now like to introduce today's speakers. As mentioned, Ed Kuzemchek is Chief Technology Officer, Director of IoT, and founder at Software Design Solutions. Ed has been creating embedded software solutions for nearly 30 years and was the president of Software Design Solutions for more than 13 years. The company provides embedded system software development, desktop application development, and software process improvement consulting. We're also joined by Jeffrey Young, Head of Business Development Americas at Stratus Technologies. As a strong sales professional, Jeffrey has an extensive history of working in the industrial automation and computer software industries. Throughout his career, Jeffrey has demonstrated skills in negotiation, sales, customer satisfaction, sales operation, and sales management. We'll begin with Ed's presentation. Gentlemen, welcome to today's webinar, and please go ahead.
Thank you, Kevin, for having me on. As Kevin mentioned, my name is Ed Kuzemchek, and I'm CTO here at Software Design Solutions. We're an embedded system consulting company, primarily in IoT, fog, edge computing, and some cloud. Let me just talk first about what we're going to be talking about. Kevin mentioned some of the high-level glossary concepts here. We're going to be going through the industrial IoT architecture, talking about what it means to be cloud processing or fog processing, edge processing, what sensors are involved. But we're also going to be talking about what makes industrial IoT unique, what makes it different from, say, consumer IoT or retail IoT, and where in that architecture is the right place to do the various processing that you need to do to keep an industrial system running at its best. We're going to go through 4 use cases and talk about how those use cases and their unique requirements might affect the IoT architecture itself. So let's start by diving right into a nice 3-level picture of IoT architecture. So down at the physical layer where sensors are reading physical things from the devices, you have individual sensors. They might be sensing temperature or pressure or vibration, and they might be very simple. Or they might be much more complex sensors, like a LiDAR system that might be on an autonomous forklift or a security robot in your industrial factory. Those sensors are collecting data all the time and sending it usually to a gateway system. And we're going to be talking a lot about this middle layer. But in this very simple IoT architecture, just consider the gateway as something that is collecting data and sending it on to the cloud. And in the original IoT architectures, some of the first generation IoT architectures, that's all that gateway did. We're going to be talking today about so much more that can be done at that level to increase the processing that can happen. So up at the cloud, here's where you have all your fancy data analytics, maybe some machine learning, some user dashboards, and all those things that you think of when you start thinking about what IoT's return on investment is. You know, things like visibility and efficiency, preventative maintenance. Those are where you see the results of those things. But you have to keep in mind about all the hard work that's going on underneath and down at the sensors and also at the gateways. So let's take a look at the relative strengths and weaknesses of each of these layers. And there's a lot going on here, so I'll be taking a little while on this slide. So first, consider latency. So latency is the amount of time it takes from when something happens, something happens in the real world, like a pressure changes or a temperature changes or a solenoid trips. From that time to when it can be recognized, acted on, and something done to the system to apply a change. So that latency, if the sensor itself is dealing with it, it's very fast. But if that has to go to a gateway and back, it's a little bit longer. If that message has to go all the way to the cloud and back, it's a lot longer. And that's exactly why, for the last 30 years, these industrial systems have been handled by on-premise, SCADA systems or some kind of closed-loop control system where you can read these values very quickly, react to them, make changes, adjust, and continue to keep the system running. So latency is very low when you're on the machine, a little bit more if you're right next to the machine on the gateway, and a lot more if you have to go to the cloud and back. Bandwidth is very similar. I mean, you may think of the internet as having a lot of bandwidth, but in reality, at the individual machine, you could have Ethernet there, you could have fiber optic there. You've got a lot of data flying around, and you're not going to move all that data to the cloud and back in order to get the control to happen. But let's take a look at processing power. So processing power is the amount of, basically, if you think just CPU power, but it might not be a CPU, it might be an ASIC or a GPU. But processing power is the amount of compute resource that you can apply to the problem. So here our red to green bar kind of flips upside down. Down on the machine, it's not as likely that you'll be able to spend the kind of processing power to apply there as you might at the gateway, or even so more at the cloud. And the reason is, at the machine itself, you might have to run on a battery, for example. And so that's going to limit the amount of processing power you have. You might be in a harsh environment, and that's going to limit the amount of processing power that you can put there. At the gateway, you have a good deal of processing power available. And so systems like Stratus, you can put a lot of processing power right at that gateway. But certainly at the cloud, you can have as much processing power there as you can afford to pay your cloud vendor. So that does allow you to have a lot of processing available. Let's consider the next item here, which is context. So context has to do with what information do you have in your hands to make the decision on something. So if you're an individual sensor on a machine and you're sensing temperature, and there's a sensor next to you that is sensing pressure, those two sensors aren't talking to each other. They don't know what each other are saying. And I would also say that if you have designed your system such that they do, it's probably a poor design. So those systems are just doing their own little job. And so they don't have any context of each other. So up at that next level, though, you may have a gateway receiving information from 5 or 6 or 10, it's 10 sensors on an individual piece of machinery. And it has more context. It can start to make have a larger understanding of that system. It can look at the pressures, it can look at the temperatures, it can look at vibrations, and it can start to build this information together. It has more context. Now, I would also claim that up at the cloud, you have the most context. Here's where you can look at that machine versus that machine a year ago, or that machine versus the machine in a similar factory halfway around the world. And you can start to build a lot of information data models, and this is where machine learning comes in, and we'll be talking about that in a minute. Lastly, communication reliability. So communication reliability really has to do with fault tolerance. It has to do with being mission critical and life critical. And so, in terms of the sensors themselves, there are a lot of wireless sensors out there. I would claim in industrial, there's a lot more wired sensors out there. And so the reliability of that wired sensor up to that gateway is very high. And even in wireless realms, the reliability of those wireless sensors are often higher than the reliability that you can count on from that gateway up to the cloud and back. So as you start to look at this, you see that the on-machine sensors, the things way out at the edge, are good at some things and really not good at others. And similar in the cloud. But what we do see is this middle layer, this on-property, this gateway layer, is kind of a sweet spot. It is a place where you can apply a good bit of compute power. And it's also a place where you have access to enough data that you can make some interesting conclusions. So let's look at how you take advantage of that sweet spot. So one of the ways is you move some of that processing that you would be thinking about doing up at the cloud down to doing it on property. And so that's processing like machine learning. That's processing like doing potentially some pattern matching, some filtering of data. So by doing that, you can start to take advantage of this location of data that you have access to enough data to get the job done, and also this quick latency that you have. So you already, in a lot of industrial systems, are doing fast loop control in some kind of SCADA system. And I would claim that IoT systems and SCADA systems don't have to be divorced from each other, and I don't think that IoT is going to replace those fast loop control systems. But I think that what it does is it allows you to do a better job in terms of augmenting those systems and giving them new information, and also taking some of the data from those systems and making new conclusions from them. So in terms of machine learning, you might train your machine learning model offline, and a good bit of that machine learning model might run on the cloud to compare, for example, this month's data and last year's data, or look for preventative maintenance types of things. And those types of things will continue to run in the cloud because they need large data sets with a lot of context over a lot of time. But I would claim that on property, there's a lot that can be done by moving some of that machine learning pre-trained down to the on-property system and just sending it rules updates whenever you need to. So in terms of other processing that may be machine learning or may be heuristical, things like pattern matching, things like image processing, and a lot of filtering of data. I mean, if you think about it, one of the most important things that a gateway level can do is filter the data. I mean, if you have a sensor, maybe it's a temperature sensor and it's reading, once a second, and it's getting a value once a second, that's 86,000 readings a day. You don't need to send that much data up to the cloud. And you may not want to have a sophisticated enough data sensor itself to do the filtering and the min and the max and the average and all of that, because that sensor might have to be very ruggedized, and you might only have one vendor you can buy it from as a result. So doing that level of filtering, pattern matching, data reduction at this gateway level is very useful. So let's take a look at 4 different, I'll call them use cases. They're called examples here. So first, oil and gas. In this environment, the sensors have a pretty tough job. I mean, they are in a very harsh environment. They might be remote, out in the field where they have to run on battery, and they may have limited connectivity. They might have cellular, or they might have to go satellite. They certainly aren't sitting there running, in a lot of cases, on nice, clean AC power and have an Ethernet connection. Sometimes they are inside of a compressing station, for example. But in the middle layer here, say a pumping station, there might be a lot of different legacy systems that your IoT system has to connect to. And the other interesting thing about oil and gas use cases are they are very long-lived equipment. And you're not likely to be able to roll in with the world's best IoT system and say, if you just adopt this, it'll be great, but you have to replace all these pumps and all these valves and all these pipes to do it. That's just not going to happen. Those things have been there 15 years. They're going to be there another 15 years, and they'll still be running great. And so you have to think about retrofitting those systems with an IoT environment. Up at the top layer in oil and gas, this is all about efficiency and safety. So getting visibility on the whole distribution system achieves both of those goals, and you want to keep the system at peak utilization. Here's an example in life sciences, specifically pharmaceutical manufacturing. So here, the on-machine sensors are a little different. They're not likely as harsh of an environment. It's more of a laboratory condition, but they're probably a combination of off-the-shelf sensors and custom sensors, depending on the environment. And it's not so likely that the sensors will be battery powered, but they do, and they are likely to have good access to communications here. In the middle layer, where you're doing gateway level processing, it's all about process control. It's all about keeping things at exactly the right temperatures for exactly the right times and doing very precise measurements. So up at the cloud level, it's very similar. You're doing very precise control, and so you have to have compliance against that control. You're doing you have regulatory matters, you have chain of custody and provenance to worry about, and so this is where things like blockchain technologies might come into play. It's not so likely that you're going to have communication difficulties here or power level difficulties here like you would in an oil and gas situation, but you have very precise measurements to make. And you have an interesting chain of custody, as I mentioned, and an interesting calibration set of concerns. So let's consider a utility example. Here again, mission critical. Utilities are a life critical, mission critical system. They are a mixture of old and new technologies. I mean, you might have everything in one system. You might have everything from a coal-fired steam power plant to a solar cell microgrid with smart meters in the same exact system, and it all has to work together. And so you might have everything from people getting their, selling energy to their neighbor to someone has to run out and read a meter because that's the only way the meter can get read. So the focus here is on improving efficiency, lowering environmental impact, and keeping that same fault tolerance that this system has had since it was first built 100 years ago. So out in the field, you might have your smart meters, occupancy and demand sensors, and this is all about measuring use, but also trying to reduce waste and trying to match the supply to the demand. And so those types of systems, have to remain working, but also contribute more than they've contributed in the past by reporting up, for example, occupancy in the building. In the middle layer, here's where a lot of the new technologies have come in. Things like microgrids, things substation management, where you can start to have more load balancing going on at the substation level, as well as bringing in alternative generation. The top level of the system is all about monitoring the entire health of the network. And these are the kinds of systems where proper load balancing has to get done. One part of the system could very badly interact with the remainder of the system and take it down. And so you have to have this fault-tolerant system which reacts very quickly, but in a way that keeps the whole system working and efficient. The final example here is transportation. And this is another century-old set of technologies that are out there. It's auto and truck and rail and air, and it's roadways that are centuries old now, and as well as tracks, and of course airlines and shipping lines. So out at the very edge of the system, the main concerns here are safety and navigation, dealing with congestion. So you have sensors to monitor rail and sensors to monitor roads, and of course GPS and LiDAR and cameras and everything that is required to do that monitoring. The difficulty here is this is a very large, sparse, diverse, harsh environment. So putting us, smart roads is a great thing to say, but when it comes down to it, I'm here in Pittsburgh, Pennsylvania, and that road's going to get covered in snow for a few months a year, and it's going to get potholes, and it's going to get a plow truck run over it. And so you're going to have a very difficult environment for a sensor to live in. And at the same time, if you're going to have these smart cities with autonomous cars and great traffic flow congestion, you're going to have to build these things this way. The middle layer here, I use this to describe the actual vehicle itself. This might be the car or the truck or the train. One important difference in transportation that is different from the other examples here is at this level, this unit still has to be fully capable of operating without a connection to the cloud. So, for example, if you have an autonomous car, for example, or an autonomous truck doing a delivery for your factory, if the cloud connection goes away, that truck just can't stop right in the middle of Interstate 80 and come to a halt. It has to continue on until the cloud connection comes back. And so it has to be tolerant of this connection of the cloud going away. So it has to be quite autonomous in terms of its own navigation, its own safety, its own ability to interact with other vehicles. Difference here is it's likely that most of the time there's plenty of power available to the sensors, although actual sensors on the roads themselves, they still might have to be battery operated or energy harvested or solar or something like that. So what we've seen in comparison and contrast here is I think that each of these systems has their own mission-critical, life-critical requirements, but the way that those requirements manifest themselves really turns into requirements for your IoT system. Maybe the sensors have to be very capable of operating in a harsh environment, which may limit your choices on sensors, which may limit the amount of processing you can put into a sensor. Because in a lot of these situations, when you go out and you start looking through your catalog, you're going to find that there might be 2 vendors that make the pressure sensor that will actually work in your environment because you have, explosion-proof requirements or something like that. And so the processing, asking those vendors to also include a bunch of processing at that level just doesn't make sense. The other side of it is I like to think of IoT as a pyramid where you have many, many sensors at the bottom and then a lot fewer gateways and a lot less cloud interaction. And so when you think about it, you don't want to put a lot of cost into those sensors, but that second level is the sweet spot, as I mentioned, of doing this processing so that you can collect data at the bottom level of sensors, push it up to the gateway, and have the gateway there doing a lot of that processing that I mentioned earlier, having it doing the filtering, having it doing the pattern matching. And that is the takeaway that I want to bring out here. So specifically, in recap, we talked about how to segment our processing to match this intersection where the data is available and the compute power is available. And so specifically, we mentioned edge compute, or that middle layer, that gateway layer, is a sweet spot for a lot of this different processing that you might think about doing. It's really the case that out at the sensors, you don't have enough data or processing, and up at the cloud, you can't afford to send all the data there and back. So each of the use cases that we mentioned has different requirements, but they share a lot of these same similarities. So I want to hand it over to Jeffrey to continue on, talk about Stratus.
Great. Thank you very much, Ed. Everyone, for those that might have missed the introduction, my name is Jeff Young, and I'm with Stratus Technologies. And first and foremost, I want to thank Ed for everything that he just covered right here. And I want to add to it that, so often the question comes up is, really what is the edge? And I think you did a great job of touching on, the difference between the sensory edge and edge compute. And it's a question that we get quite often at Stratus as well, where is the edge? And a good answer is that the edge really is in the eye of the beholder. But at Stratus, what we found is that the edge is the point of aggregation for data in the field. And another thing that we found is, the strength in that data really is close to the source where the real-time decisions are made. Whether that be a remote pumping or compression station for a pipeline, or, it could be a individual production line at a facility, or, it could just be a normal industrial or commercial location where compute infrastructure is required, but the manpower or the skill set is limited at best to support the operations. And then also you have to take into consideration, operational requirements when they come into play and when defining what that edge is. And as Ed addressed earlier, this could determine if the edge is an extension of cloud activities or if it's an extension of control activities. But today, what we'll focus on is we're going to take a look at this graph, and we're really going to zero in on the middle 2 silos here for our edge computing architecture examples. So as you see here, basically we're showing a segmentation for a remote location or a production line use case. And in this example of edge computing on a production line for a dairy facility, as it's shown, it highlights a typical use case that we see across many industries that our solutions here at Stratus serve every day. Whether it's a production line like shown or a remote location such as a pipeline or rail like Ed covered earlier, or so on. Although the locations and the industries will differ, the typical IoT use cases usually have a similar set of both environmental and compute requirements that we must all meet. First and foremost, our customers are usually looking for a solution that gives them a highly available virtualized environment, and it allows them to support multiple applications or virtual machines. And you'll see those highlighted here as VMs 1, 2, 3, and 4. And what they want out of this as well is they want little to no unplanned downtime. And this is very important as companies embrace and execute their own digital transformation initiatives. And that's because at this point, when they're doing this, data becomes absolutely critical. Next, our customers are also realizing that as you get away from the typical enterprise data center server rooms, these new compute environments introduce the harsh conditions that, once again, Ed just touched on earlier. And once you're introduced to these harsh conditions, a ruggedized design for your compute solutions needs to be implemented, especially when you start to take into consideration the different variables around humidity or heat or dust or so on. And then lastly, what we found is that you really need a solution that's simple. It needs to be both easy to implement and easy to service. Because this is where more than likely you're going to have a small to non-existent concentration of IT personnel to support the solution. So you'll need an architecture that can be deployed by either IT or controls professionals and has thought through the importance of device security. So this is why Stratus developed our edge computing platform, and it's what we call the ZTC Edge. And it's shown here in the picture to the right, directly above the controller. And it's really what it is. It's a robust, redundant, ruggedized edge compute solution that was designed with simplicity as a key feature, but still capable of tackling all the requirements that I just went over. Next, we're going to go over to the what I call the third silo. And this is going to take a look at a use case for a segmentation of a plant or a facility. All right, so this example it's more of a what you would call like a remote plant or remote facility deployment for an edge computing use case. You'll have some similar requirements here from our previous example, specifically around the virtualized environment. But this is usually a more robust offering that is needed. I mean, both in memory and in storage. And since these instances are typically hosting more virtual machines, and their need for compute power is greater, they will require more of a data center clean room location for deployment. And this is ultimately it's a byproduct of the design of the hardware and the type of environment that's needed for operational efficiency. But once again, one feature that is always helpful for either type of use case, this one or the one previously, is an architecture that is simple. Because even here in a remote plant or remote facility, you're normally going to have a small concentration at best of IT professionals, and sometimes no IT support at all on site. So again, you need a solution that's powerful enough to run your applications, but simple enough to service that any personnel on site can support it. So what we like to say is that this type of application or this type of deployment is where unplanned downtime is just completely unacceptable. And this is a perfect use case for what we call the FT server here at Stratus. And the FT server, it's a fault-tolerant edge computing solution that's capable of executing your plant-wide edge computing needs, but still designed with operational simplicity and longer life cycles in mind. And after deployment, it's easily serviced by any personnel that are on site, whether they have an IT background or not. So on this slide here, what we're going to touch on is these are the 3 steps to simplifying, computing at the edge. And when you're considering computing at the edge, first and foremost, you have to get connected. If you're not connected, you can't take advantage of the data at your assets. And secondly, as you go on this journey, we urge you to rethink your infrastructure. Really take a look at what are the requirements for your compute environment, and how do you plan on addressing those? You know, is our environmental concerns something that you need to look into more, or is it a situation where, you know, this is an instance where this is what we would call a plant-wide execution of edge compute, and you need to consider more of a data center server-style solution? And then lastly, you know, you must develop an architectural strategy around your needs. You know, you need to decide where your edge computing strategy will be implemented, and is it going to be part of the control activities, or is it an extension of your cloud activities? So what I'll say is, you know, there's no correct order, but they all must be done. I mean, these are 3 steps that you will need to address at some point in time. And then finally, you know, here at Stratus, we believe that as you implement an edge compute architecture design, you know, you should also consider these key design principles into that plan. You'll see them listed here to the left, you know, that revolve around virtualization, high availability or fault tolerance, obviously operational simplicity, which I covered a couple of times, and then overall system lifespan. You know, because one of the things that we really hang our hat on here at Stratus is that, you know, we don't have the typical lifespan from a compute environment that some others in the industry do, and it's really a key feature and a key benefit for a solution from Stratus. And when you look at all of these here listed to the left, you know, all of these are inherently available and designed into our edge compute solutions, because ultimately that's what Stratus has been known for almost 40 years. You know, we build the most reliable computing platforms for your enterprise or edge computing needs. So to wrap this up, you know, if you like this topic, I'd urge you to take a look at the research done by IDC. You know, it's titled Highly Available Edge Computing Platforms Accelerate Industrial Automation. And then also, if you'd like to speak to someone from Stratus specifically about your edge computing journey, you can reach out to Greg Payton. His information is shown here, and he will connect you with your local contact from our team. So, Kevin, I believe it's back to you now.
Well, thanks so much, Jeffrey, and Ed as well. Please send us your questions. I'm speaking to our audience now. Please send us your questions. We already have some, and we're going to break into those right now, but we'd like to see more. Before we start the questions too, there's been some confusion in terms of downloading the slide set and the CEU. If you're not able to access it, we'll send instructions or an alternative method for doing it in our follow-up email. I have a question that's just come in from one of our listeners, and I'll address this to you, Ed. How is edge computing different from a distributed controls computing architecture? For example, cell controllers and area controllers on the plant floor were very similar to the edge, and they've been around for decades now. I guess they're questioning whether edge is really something new. How would you answer something like that?
Thank you, Kevin. I don't think there's anything new in technology. I think that everything is a growth out of something else. But you know, I think that the way that edge computing is different from the closed loop control, be it distributed closed loop control from before, is that edge computing is there for the purpose of bringing that data to the next level, up to the cloud, where it can be utilized in these larger context systems, where you can take that data maybe from the plant that didn't ever leave the plant earlier, and start to compare it to, well, wait, why is this same machine working so much better in my plant over here in Des Moines than it is over here in Indianapolis? You know, why are those two machines running at a different level of efficiency? And I think that the actual actions that they're taking are very similar. I think that they still have to be robust and reliable. They still have to be able to run in a distributed environment. They still have to run if someone severs the internet link out of the building. The plant can't come to a halt just because they lost their communication up to the cloud. And so in that way, they're very similar. But in another way, the purpose is to gather that data in a way that it can be made available up to the cloud.
Well, thanks, Ed. Jeffrey, a question for you. One aspect of IIoT and cloud that we haven't mentioned very much at all yet is the explosion in analytics, machine learning, and AI that is about to contribute so much to the world of automation and information technology. Do you think, is it such that using fog computing or cloud computing or both makes it easier to begin to apply analytics? And just give us a little bit of background on the context in terms of analytics in IIoT and cloud endeavors.
Yeah, so what I would say is, when it comes to edge computing or fog computing, specifically around analytics and how that relates to the cloud, I think what you'll see is a mix. I think you'll see the edge computing used as more of what used to be called like a data concentrator or a local deployment for multiple applications that the users feel need to be running either close to the source, on the machine, close to the machine, and pulling that data in, aggregating that data, and then sending it to the cloud for the analytics to be done off-site in a non-harsh environment. So I think ultimately, as people start to look at their architecture of how they design their solutions for either their facilities or their locations, however you want to define it, I think your architecture, if analytics and machine learning is something that you want to do, I think you need to plan for both. I think you need to plan both for an edge compute into your architecture, and I think you need to plan also for some type of cloud architecture to be involved in it as well.
Thanks, Jeffrey. Ed, if a company sets up a fog computing environment, will they need to have special skills in-house that they wouldn't need in an entirely cloud environment or in an on-premises environment?
Fog computing is different because of the requirements that you have and what you have available to use. Like, for example, if you're going to do a fog computing machine learning environment or a fog computing image processing, if you're in the cloud, you may spin up a whole bunch of microservices, or you may spin up a whole bunch of CPUs and just go at it that way. But in a fog environment, you're still in a constrained environment in terms of the amount of hardware resource that you're using there. Now, granted, that hardware resource might have some GPUs, it might have heavy-duty processors, but the approach you take is more of an embedded systems approach when you're doing fog compute. I don't want to say that cloud computing isn't about efficiency, but it's a different way of addressing efficiency, where you have a very limited, defined set of compute capability when you're working in the fog. So the way you go about assigning the resources, the way you go about making trade-offs is different.
Thanks, Ed. Jeffrey, many people that I hear speaking about IIoT have said that it primarily is going to be a greenfield environment. In other words, working on new means of production and not necessarily those that are already in use. Is that your take on it? And how is the thinking on that changing, and what do you foresee?
Yeah, thanks, Kevin. That's a great question. So what I would say is yes and no, right? When you start balancing out the greenfield versus brownfield discussion, is it easier to design an architecture holistically from an IIoT perspective for a greenfield? Yes, absolutely. But what I would argue is that there are many more brownfields that are already in use, and so the greater return on investment would be from a brownfield IIoT deployment. And I believe that it's not as difficult to achieve. Simply, and actually Ed touched on it earlier in his slides, when you consider it from a retrofit, or what I've even heard called as a bolt-on solution for edge computing, which honestly it falls right in line with the ZTC Edge that I covered earlier, that is a solution that you don't have to have a very intense design stage for the architecture to get the advantages from edge computing from the ZTC edge, whether it be a brownfield or a greenfield deployment.
Good. Jeffrey, another question for you. I mean, I think to some degree related. When someone goes out and buys a control system, they know what they're going to do with it. They're going to control a process that's well understood. But the thing about IIoT, it can be applied in so many different things and in so many different ways. How would you advise somebody who is interested in IIoT and these more sophisticated forms of control and data management? Where would you advise them to look for their initial application?
Yeah, so what I would say is the immediate return, what you would say the bang for your buck is going to be your most critical processes or applications or portions of the plant, because it's the most critical ones that are the ones that you can't have go down, and usually the money makers for your organization. So as you look at these type of applications, if you're trying to put together a proof of concept or something like that for an idea that you have around that, I'd say do the research on which solutions make the most sense for you, and then build a business case as to, okay, what portion of my facility, what portion of my plant am I going to show the quickest and the most robust return on investment for this type of deployment.
Good, thanks. Ed, question for you. What about the role of open source? It wasn't that many years ago when people said that open source was never going to play a big role in the process control and industrial automation realm. That certainly has changed. But specific to IIoT and the kind of computing we're talking about today, what do you see as the role for open source?
I think there's a broad role for open source in IoT and IIoT, specifically in open APIs and all of the libraries that are around supporting an open API. I mean, so when you have something like MQTT, I certainly wouldn't go and write from scratch an MQTT broker or an MQTT client. And in a lot of situations, we're willing to use the open source, PayHo library or something like that to talk to an MQTT broker, because that's a very standard, a very robust, a very well-worked system. Now, in some situations, you may have systems, architectures, which have been highly optimized with a proprietary implementation, but they're still using an open API. And so I think that open APIs are critical to IoT expansion, but open source also plays a very large role.
Good. Thanks, Ed. Jeff, here's a question near and dear to the heart of any salesman. Does Stratus provide full integration or just hardware-software integration? And part two, what software, if any, does Stratus offer to run on their hardware and in order to set up a complete IIoT solution?
No, great question. So what I would say is here at Stratus, we provide the hardware and the solutions for your edge computing needs, and you can break those down into a couple different silos, whether it be, highly available or fully fault tolerant. But on those solutions, we really are software agnostic. So we don't provide the actual software ourselves unless, you're talking about the virtualization layer. But, when it comes down to what applications you're trying to run or which applications you intend on running in your plant locations, yes, they will run on our hardware, but it's something that we do not provide as part of our solutions.
Good. This is an interesting question. I'll give it to you, Ed, for a try. And one of our listeners is asking, is there any work on sensors that you know of that includes within the sensor itself the kind of context that would be needed as the data ascends upwards in the automation triangle?
Well, there is some work on that, and I mentioned before that industrial automation is hard to do this because the sensors often have to live in very harsh environments. But there's as compute technology gets more power efficient and you can squeeze more capability into a smaller, more power efficient package. There's a number of the silicon vendors, the silicon manufacturers who are starting to put, neural network capabilities into very small, $1, $2 kind of processors. And so that's where I would say that you may not be able to reach over and look at the context of the sensor beside you, but you may be able to run simple pattern matching, for example, inside that sensor. So you could say, okay, I'm not going to record all of this vibration and send it up to the gateway. I'm just going to look for a vibration pattern that looks a little out of whack and report that.
Good, thanks, Ed. Jeffrey, one of the most fascinating aspects of these endeavors is the relationship between OT and IT, and that's already been mentioned. Just to make a quick personal observation, it used to be that the OT guys would complain that the IT guys were trying to make all the decisions. I went to a forum just recently in which they said to the OT guys, come on guys, be nice. Bring the IT guys in from the beginning. Don't just tell them what you're doing at the end. So there's been a real revolution there. One of our listeners asked, as we move upwards from plant floor to cloud, does it become more software intensive in that it will have to be in the hands of IT specialists?
What I would say is, I've seen this pretty extensively. I would say probably over the last 18 to 24 months, is that a lot of organizations are creating this, subset within their organization of an IT OT convergence group, and it's typically, it's based around people that they think, and it's crazy, is that they think that can communicate the best. Because ultimately that's really what you need is a team that can communicate and can create a cross-functional team. And it's because at the end of the day, if you look at the two primary concerns that usually cause the IT and the OT groups to butt heads, it's that, from an IT perspective, one of their primary, or if not most primary concern is security. And then past that, it's availability. Well, it's the complete opposite from an OT perspective. Their primary concern is availability because that's directly related to production. And then security is also part of that, but not as critical as availability. So at the end of the day, I think, to answer the question, I don't think it's going to be pushed up to IT specialists specifically, but I do think you will see more cross-functional teams where the IT and the OT people are what I like to say, playing nicely in the sandbox together, per se.
Good. Thanks, Jeffrey. Ed, one of our listeners is asking about IIoT as a two-way process. In other words, most of our discussion today has been about pushing data from the plant floor or the process up into the enterprise or wherever it's destined for. They're asking about what about sending things back down to the floor? Is there logic control that can be enacted? Are commands from PLCs or SCADA? What about that downward direction?
Yeah, we do see that in systems that we build, primarily in many of the IoT systems that we build. We're sending dynamic configuration information back down to the sensors because you may configure a sensor to read at a certain frequency. Maybe it's once a second, maybe it's 10 times a second, maybe it's once a minute, whatever. But then, as part of the deployment, you may decide, in certain situations, I want that sensor to read at a different frequency. And that's where a protocol like MQTT, for example, works very well because it's a publisher-subscriber protocol. The sensors can publish to their data topics and send data up, and they can subscribe to configuration topics. And so if the gateway or even the cloud wants to reconfigure that sensor, it simply sends it a message on its configuration topic saying, things look a little weird. Maybe we should have you reading a little more often and let's collect some more data.
Great. Ed, let me ask you a follow-up question to that one. Besides MQTT, what are some of the most important protocols that have come to the surface as IIoT has been instantiated?
So the wired protocols are often the same ones that have been in use for quite some time in industrial. You know, you have your CAN bus and your RS-485, and so those are still around and they're alive and well. But then as you start to send data over TCP, whether it's locally within the plant or up to the cloud, the most important thing I would say is, boy, don't go and invent a new protocol. Look at the ones that are out there to see if they meet your needs. And MQTT is very important for this. CoAP is a similar type of protocol. I would say that MQTT has a little bit larger following. And of course, HTTP REST is also valuable in a lot of ways because, one, it's common and everyone understands it. It's a little heavier to send small amounts of data, but it's very useful for communicating with existing cloud-based systems. And so you may do an HTTP REST post call, for example, or a GET call to push or get information. It's not likely you're going to do that to send, 2 bytes of temperature data. MQTT might be better for that. But if you are working with an existing system that already talks REST, it's a great way to go get data from it.
Great, thanks, Ed. Jeffrey, there's been a lot of discussion about the need for data wrangling in various types of IIoT projects, and that over time, if you're going to be doing machine learning or AI, unfortunately, over time, the way data was handled evolved on any given installation, and it's not normalized enough for use. Maybe you could talk a little bit about whether you encounter those kinds of problems in real-time applications, and if so, how difficult it is.
Yeah, I think this was somewhat kind of addressed on a question I had earlier, but basically what I'm seeing more than anything is that from an edge computing standpoint, the aggregation of data close to the machine is key from an edge compute, and then what you do with that data after you've captured it is really how you design your architecture. Whether you want that to be kept on premise to manipulate or learn from it whichever way that you want to, or whether you're wanting to integrate a cloud solution into part of your architecture, so that once you, for the word that you use, wrangle that data and really kind of wrap your arms around what your process or your machine is doing, how do you want to implement some type of analytics or machine learning type solution to that data. But once again, I think when you look at edge computing, I think as we've defined it earlier, I think the edge computing is the point of data aggregation, whether it's at a remote facility or on a production line, is how we kind of describe it.
Good, thanks, Jeffrey. We've only got a little bit of time left. We'll have one question for each of our panel members. Ed, how enthusiastic is the engineering community about moving beyond their reliance on spreadsheets and embracing analytics? Should anybody who has some background in statistics be able to get started without having the support of a data scientist necessarily?
Yeah, Kevin, I think that specifically if that individual is already familiar with their domain, if they're a process control engineer or an automation engineer, and they understand very well their domain, that's the largest part of the problem. And if they additionally understand a little bit about statistics, it's not too great of a leap to start looking at and talking to data scientists. I wouldn't say that they'd be able to necessarily take on the whole thing without even consulting one, but they would have all of the tools that they need to sit down and have a conversation about what parts of the data do they normally look at, and that data scientist can bring in their expertise and say, well, here's different ways that you can look at that data that you might not have thought of before.
Well, thanks, Ed. Jeffrey, the final question is for you. Based on the use cases that we looked at during the course of the webinar, what kind of challenges would you anticipate those embarking on IIoT projects would primarily encounter as they begin?
Man, that's a great question. I think probably the biggest challenge is overall buy-in. You know, whether it be from an organizational structure, or if the organization itself is kind of pushing the initiative down from the top down, getting buy-in from the key players out in the field that this is the direction that the company needs to go to stay competitive, or whatever whatever situation that company or that organization has deemed is the main reason they're doing this. But I think you have to have buy-in from both sides, because there are many use cases out there, and Ed covered a few of them earlier. There are many use cases out there where you can execute this and it can make a big impact to your organization. But to do that, you have to absolutely have everybody on board with the initiative.
Great. Thanks, Jeffrey. That's all the questions we have time for today. Thank you to our expert panelists, and thank you all for attending today's webcast. We hope it suited your purposes. For more information, go to the website link noted in the interface. I'd like to thank Stratus Technologies for sponsoring today's webcast, and now that we're just about done, we want to hear how we did. The exit survey will pop up on your screen as soon as the webcast ends. Please take a moment to complete it, as we use this information to improve our webinars. On behalf of CFE Media and Technology, we'll see you next time.